All right, ladies and gentlemen, the class recording has started. So, on Friday, we discussed the simple pendulum, and we said that a simple pendulum is an example of periodic motion in that it has a restoring force that brings it back to the middle. What provides the restoring force? Gravity. But we talked about that it's not exactly all of gravity, right? That it's only a certain component of gravity. And, nope. So there's that. So we talked about the idea that gravity always points straight down, but because the object is not moving straight down, part of that component of gravity brings it back towards the center. Yes, ma'am?
From the lab, I had a question like, how would this be different if it was like on the board?
Okay, well let's...
like no air resistance on
Gotcha. So we'll get to that. That's kind of where we left off on Friday, so let's review this quickly and then we'll get to that. Alright, so component of gravity brings it back to the middle, and that means it keeps repeating over and over and over again, and that makes it periodic motion. But we talked about the idea that technically it is not simple harmonic motion. Okay, so we should change this here from with to almost simple harmonic motion, because the requirement for simple harmonic motion is that the restoring force is proportional to the displacement, which is true on something like the rubber bands when they're pulling the car back to the middle because of Hooke's law. But here, because of the whole gravity component thing, that's not the case, right? That it's proportional to a component of gravity, not all of gravity. Okay? So, up here on the front, I gave you guys two pendulums, right, to illustrate the one point that we spent a good amount of time talking about yesterday, right, or on Friday. And what is that one point that we talked about on Friday? I guess we should say the terms that we've introduced with simple harmonic motion, period, frequency, amplitude, they can all be applied to this, right? And this one is illustrating something about the period. What did we learn about the period of a pendulum on Friday? Remember? Determined by length, right? That the length of the pendulum is really what determines its period, right? And so here we have these two pendulums, one short, one long, right? We see that the period of the shorter one is shorter, right? Is a smaller amount of time than the period of the longer one. And doesn't matter whether we change the mass, it doesn't matter how big of a swing we take, the amplitude of the motion, that the length is really the only one that makes an appreciable difference in the period of the pendulum. Okay? Good there? All right. So, Ben, let's talk a little bit about your question, because that gets into this. Technically, according to this formula that's up here, length is not the only thing that affects the period of the pendulum. What else affects the period of the pendulum? The acceleration of gravity also affects the period of the pendulum. So on Friday, we left off with this picture. And here's a picture of Ohio, and it's a gravity map of Ohio. Places that are in red technically have a higher gravitational, or a faster gravitational acceleration than the areas that are in blue. Okay? Now, even though we put those different colors on the map, the differences are so small that it really that you wouldn't be able to measure any appreciable difference, at least not with the stopwatch on your phone. If we were really precise and had like a stopwatch that went out to like 7 decimal points or something like that, then we might be able to measure a difference, okay? But there are other places in the universe that have different gravity, right? So if we took this pendulum to the moon, right, it would go back and forth, but we would see an appreciable difference in its period, right? So if we take a look at the formula for the period, right, T is equal to 2 pi times the square root of L over G. What do we know about G on the moon? It's decreased, right? So if we decrease the gravitational acceleration, what's that going to do to the period? It's going to increase the period because we have g on the bottom of the fraction, right? Also, if we think about it just from the standpoint of if gravity is the force that brings it back to the middle, if there's less gravity, less gravitational acceleration, it's going to take a longer time to bring it back to the middle. So we could take this same pendulum, set it up on the moon, and we would see the period increased. They would move more slowly back and forth across from one side to the other. Okay? Good there? Now, transitioning into some newer things that we're going to finish up today. Okay? Eventually, what happens to these pendulums? They stop, right? Because why? Heat, friction, right? All those things that take mechanical energy and turn them into non-mechanical energy, right? Heat energy specifically, right? If we could get rid of the air resistance in this room, this pendulum would go longer. It would take a longer time for it, but it would still stop eventually because we got some friction up here at the pivot point and stuff like that, okay? If we could set up a pendulum that has no friction, has no air resistance, but the gravitational acceleration is still there, it would just continue to go back and forth and back and forth the same height each time. So the amplitude would never change. Okay? Oh, one thing. So, as we go through and do this, okay, the amplitude of the motion decreases. The distance that it moves from the equilibrium point keeps becoming smaller and smaller and smaller and smaller and smaller. And we have a name for that. It's called damping. Okay? So if we take a look here, and I believe this picture is on the back page of your,
Wait, did you move it again? It's still going like that ever
It's
since
still
the
going.
morning?
No, I started again since the morning.
So you started only once?
No, I started it a couple times. No, not really. Because even if we put it like in a vacuum chamber that didn't have air resistance, we would still have some friction like up at the top. So it would take longer before it, but it would still stop.
So basically,
I mean, we could try as much as we could to reduce the amount of friction. Yeah, I mean, we could probably make it go a long time, but I don't know if we could make it go forever. You know what I'm saying? Because the oil is a good thing. Like making that pendulum as friction small as possible. I can't say frictionless, right? But that's what like a really expensive clockmaker, right, is trying to do with that makes pendulum that or a clock that runs on a pendulum. Because the less you lose the friction, the less chance you have of your pendulum stopping and then making the clock stop. You know what I'm saying? Yeah. So a clockmaker is trying to reduce the amount of friction as much as possible so that it takes longer time before that pendulum stops. Do you follow?
Yeah.
Good.
So what elements of the periodic table have limits?
I mean,
Like,
I don't know if there's any one element. I mean, like graphite, like with carbon, the way that carbon is set up in graphite, which is like sheets as opposed to like interconnected. We use graphite as a lubricant to reduce friction over time, especially in like industrial machinery and stuff like that. So that might work.
graphite?
Yeah.
Like lead?
Yep.
Like that
Yep.
graphite?
That's why when you rub it across the paper, it like slides across the paper and sticks and doesn't like break off because it has like lubricating. You know, yeah. So, fine, good.
Would you make a frictionless hinge with magnets?
Yes.
Like a magnet rod?
Absolutely. So if we had something along the lines, if we had like this bar and in this joint right here, there was like magnets all around it, so it never actually touched, then we could do that.
So
Would
if
you?
you put that in a vacuum,
Yeah.
would it basically go for
Yeah. So, but that's sort of the principle that a maglev train, a magnetic levitation train, works on, like a bullet train. where the magnets on the track and magnets on the train are strong enough that actually the train doesn't touch the track. And so then the only resistance that you have to work on is air resistance. Right? Yeah, they have Japan, and then I think the channel,
so
like
awesome.
I'm not sure if the one that goes between England and France is a maglev train or not. I'm not 100% sure on that.
Wait, England
That's
has
like
an
so
underwater
evil
tunnel that goes
friendly.
to
Yeah,
France?
within the English Channel.
Yeah.
So,
No way,
It's
really?
been there for a while.
it's been there for a long time.
I never said.
You ever see Mission Impossible, like the original one with
Yeah, they start with that
with
weird
Tom
guy.
Cruise? So, no, like the original movie Mission Impossible with Tom
They
Cruise.
must have
Yeah.
tried.
They have like a fight in the channel.
Was this before
So-
he became a crazy man?
Oh yeah, absolutely. So,
Before he turned to the dark side?
what was I gonna say? Oh, a couple years ago I saw this story or read something online, whatever, that they were thinking about actually doing the same thing, making like a maglev train that actually runs from London to New York, but under the ocean.
That'd be so sick, that'd be sick.
Oh my
And
god.
but to help, like to make it go like even more, is the tube that they were gonna make.
Okay.
They would like have like airlocks in it, and they would make it like almost like a vacuum. So we'd have a situation where you have magnetic levitation and no air
That'd be
resistance.
so sick.
So,
Really fast.
well,
How would they build that tunnel?
see that was the problem. Is like, okay, we have this like 3,000 mile long tunnel under the ocean. If
It's
some
so
and
dangerous.
it's a vacuum.
Yeah, yeah.
If it like springs a leak, like yeah, now we have problems, you know.
I mean,
And then
It's a
things like,
vacuum, there's no like pressure to hold it.
well, I mean, you could reinforce it, like structurally you can reinforce it because we do that all the
I
time,
think they can do it.
right? But it's like, okay, if you structurally reinforce something here and like on in the surface, air rushes in and that's okay for people. Like okay, if you're in the tunnel and it breaks and water rushes in, that's not good for people, you know. So, and also, I mean, you have to worry about things like submarines and whales and stuff like that, like running into
So like they
it.
can handle it?
What?
They can handle it?
Oh yeah, it's gonna
If you-
take a
No,
long
I
time
meant
to,
no. Like
pass.
we have to worry about whales running into
No, I
it.
know, like if you keep lights around it, the whales won't come near it.
Who knows?
They're used to deeper water, so
So
of
it's
course
kind
they'll
of
just.
just like through the water, not like underneath.
What?
Yeah, like
Yeah,
through
yeah,
the water.
it's
So it's like
armored with, like,
it's like
turrets.
anchored to the bottom.
Yeah,
Yeah.
You just put like a bridge or something.
That just sounds like a master.
Yeah. It's like I think the intent of it was it would be like anchored to the ocean floor, and then like it would be like floating. I don't know how far off the
That'd be
ocean
so
floor.
cool.
I thought you meant like under the ground of the ocean.
No.
Can we
Yeah,
look
the
at the
tunnel's
tunnel?
supposed to-
I've never seen it, I really wanna see it.
Yeah. I'm watching
London
the
to New
Japan
York,
train.
Connecting those two cities
Yeah,
would be
it's easier
huge,
than
they're like
putting it under the
equivalent to
ocean.
each other. It's like the salt mines under one here.
Yeah,
But then you have to build really
Hey guys, let's connect New York to Somalia via bullet train. Let's do this, we need it.
That'd be so awesome.
Yep, Somalian pirates, they'll have a better way to
Wait, how long is it thing?
So something like
How does
this.
it like just flow?
What?
How does it just flow?
No, hold on.
Whoa.
Whoa, get into it.
Wait, how many miles the thing?
She used to color.
Because well, but I mean, things naturally float, right? I mean, if it's more buoyant than water, right? If it just like an ocean vessel or something like that. But I think like the intent was it would be sort of like anchored to the ocean floor like this.
Also, it's like tied onto it.
anchor is.
There's no air in it.
That's true. Maybe it's a structural support.
Wait, what air are people gonna breathe?
Or maybe there's like a ring of air around it. What? I suppose if you made the tunnel wide enough, you could have two tracks in it. You know, so. But anyway, I mean, logistically, there's a ton of issues. But if from
That'd be sick.
from here,
That'd be huge.
right, from here to here, right?
So fast.
If it's magnetic levitation, no friction from surface, right? But then also if they make that a vacuum, there's no air resistance. Two things. One, you could make it go really fast, right? But two, once you made it go really fast,
Just slow down.
what would it do? Just keep going, right? You wouldn't need gas.
You wouldn't require fuel.
I mean, obviously, it would be electrical, because it'd be electromagnets and stuff like that. But once you got it going,
And how many miles is
Yeah,
that?
but they said that you said they were decisions about this.
oh yeah, this is like totally theoretical,
Yeah.
hypothetical. I mean, this would cost so much money. I mean,
And they had to meet each other, because they're gonna have to come and hit each other.
well, I imagine you probably have two tracks. You know.
Yeah, but the US got the war with
How long would it
Turkey.
take though, if like one, if like, let's say like we're going to New York, and
No.
they're coming through New York.
Yeah.
Cause like if
That would
they
take like
understand,
20,
like,
30 years.
like
Let's build that wall.
Yeah. Like I'm not sure how they would build it. You know.
It's like they go genetic.
Well, but I think though, like what we're talking about with the kind of speed that you could generate and stuff like that, you could make this trip in like 3 hours or something like that.
Yeah.
Wow.
You know.
That's pretty easy.
That's fast.
That's fast.
That's twice
Maybe
as fast
maybe
as
that's
the
an
way.
exaggeration. But, you know,
Why
it
don't
might
they
be
make it above water? Why does it always have to be below freezing water? Like, why can't it be above water?
Yeah, but
We can't float.
No, I'm saying, why can't it be like
Do it in
arched
air?
above the ocean
How are
rather
you gonna
than
support it?
pillars?
Do you know how far this is? Here.
Yeah, I asked you like 4 times. You didn't ask me.
To
Well, how
here.
do you plan on getting it suspended up there with
This
this?
is. Do you know how deep the Atlantic Ocean is?
Yeah.
It's like 6 miles
Carry
deep.
on a trench, bring it on.
Yeah.
Wait, how many miles is the whole thing from New York to London?
I don't know how many miles it is from New York to London. I don't know. I mean, it takes like
I'll be honest with
it takes you about 5 hours or 6 hours to fly from New York to Los Angeles, and that's about 3,000 miles. And I think it's a longer flight to get to London.
Carnegie built a bridge out of steel.
True.
All right, so this discussion.
He was the first person to do it.
So this discussion about the damping that led us into this frictionless surface actually leads us into this physical concept called resonance, which all of you are familiar with from your days on the playground, or if your days on the playground aren't over, you're still familiar with it. Right? So here, right, this pendulum, because of the damping, because of the loss of energy to friction, the amplitude has decreased. Now, one thing that doesn't change, though, and I wanted to make this point before, one thing that doesn't change is the period. As this thing is swinging back and forth, even though it's only swinging like this far now, okay, like a couple inches or whatever, the period, the amount of time that it takes to go back and forth remains exactly the same, because the amplitude doesn't affect the period. So this is moving much slower now than it was when it was taking those big swings. And as a result, the amount of time that it takes to go back and forth remains exactly the same. So the period doesn't depend on the amplitude, right? But sometimes
But more distance is traveled when it's like bigger.
but it's going faster. That's true. More distance is traveled when it's going, but it's traveling faster over that bigger distance. So this period and this
that is-
period is exactly the same because the length of this pendulum has not changed, right? But on the playground especially, right, we don't want this to happen, or at least the kid you're pushing doesn't want this to happen, right? Because that's not fun anymore, right? So we can keep the amplitude the same, but what do you have to do to keep the amplitude the same? You have to kick on your own, right? Or you have to keep pushing, right? Now, when you push is important, right? I can push like this, and I push like this, and I push like this, but if I push like that here, sorry.
Your weights will fall off.
If I push like that, same push, but at a different point of the swing, I won't make the amplitude the same. I'll actually hurt the amplitude, right? So that push, it's important when you get the push, right? Evan, go ahead.
When you're on a swing, how does kicking your leg make you go?
It's a Newton's third law thing.
You pick it up.
because you're like pushing against the swing and it's pushing on you, right? If you can also do it with your arms too, you know what I'm saying? Like you pull on the chain and the chain pulls on you and that pushes you forward. Does that make sense? You know? Yeah, it's totally a Newton's third law thing.
Yeah, but how is, like the internal force of the swing?
But that you like it works if you're already moving. You know what I'm saying? Like if you just sat there and you like did that, you know, it wouldn't if you sit down on the swing and start like just kind of going, it doesn't really go anywhere. You have to kind of like kick your legs too. Does that make sense? Right? So yeah, you're applying that force that just kind of maintains the momentum, right? That kind of offsets that frictional loss. Does that make sense? Right? But it's important that you apply that force and add that energy at the right interval. If you don't add it at the right time, you end up messing up the amplitude as opposed to maintaining the amplitude. We call this idea resonance, right? So the idea that you can repeatedly apply the force, and if you keep doing it at just the right time, you can make the amplitude bigger and bigger and bigger depending on how much force you apply. So resonance, this idea that we can overcome friction, but we have to keep adding energy to the system. We have to keep doing work to the system, but it's also important when we do that work to the system that causes the amplitude to maintain or in some cases grow, depending on how much work we do. Okay? Good there? All right. Tomorrow, I'll give you guys some time in class to work on these things, to work on some homework assignment, to prepare for quiz, which is scheduled for Wednesday. All right?